All right. So we continue our afternoon session. It's a great pleasure to introduce Tony Yu from Caltech, who is going to tell us about moduli spaces of non-Archimedean disk.
Thank you so much for the introduction. Does it work, the mic?
Oh, you have to switch it on.
Hello. Now it works.
Yeah.
Okay. Yeah. Let me first quickly recapitulate what we did in the morning. So we are interested in the moduli space of curves with boundaries, like this. Non-Archimedean curves with boundaries, and then we looked at some trivial examples of these moduli spaces, and we see that they behave quite badly. They are infinite dimensional, and they don't have any good properties. Then, following these trivial examples, we make an extra boundary regularity condition in order to get a nicer moduli space. And then, so it's really this boundary condition that's important for these curves. But then geometrically, we can reinterpret this boundary condition using this modified target space. If you feel that this non-separated target space is scary, you can think of it as a geometric interpretation of the boundary condition, and we use it to prove properties of the moduli space. I was also asked what's the relation between log written invariance, the punctured log written invariance by Abramovich, Chen, Gross, and Siebert. Actually, here somehow there are a lot of resemblance between this the idea of the non-Archimedean approach and the ideas from the log approach. So actually, we were all motivated by this instant of correction in SYZ river symmetry, and we want to do count of these curves with boundaries on SYZ torus fibers. But as we know, both in complex geometry or in non-Archimedean geometry, counting curves with boundaries is something hard. And the moduli spaces, they behave, they have trouble in non-Archimedean geometry, and they have also trouble in complex analytic geometry. So what we really try is to connect this count of curves with boundaries to count of closed curves. And then you can think of the non-Archimedean approach and the logarithmic approach as two different ways of turning curves with boundaries into curves without into closed curves. So in the non-Archimedean approach, what we do, as I was explaining here, is that we put a cap on that curve to make it into a closed curve. And in the logarithmic approach, what Gross and Siebert do is to shrink this circle by degeneration. So by degeneration, you shrink this circle to a puncture, and that's what they call punctured curve. Okay. That's the big picture between these two approaches. Then actually to write down any comparison theorem, it will be quite hard. Okay, so for this, so now we have interpreted this boundary regularity condition in terms of maps from this closed curve to this good target space. And and of course we now worry that this target space is just so different from the space that we we are used to work with. It's not projective, not proper, not separated. So how can we obtain any reasonable modular space? Of course, in such a target space. So this is what I will talk in this talk now. We will establish several properties of the modular space of curves in that target space, and namely, I'll talk about first boundarylessness, and then compactness, and then properness, and in the end, I'll talk about smoothness. So then we really have everything we want, and the smoothness is particularly nice, which is evident in the logarithmic story. Because when you do degeneration, you just give up smoothness. Okay, yeah. So different technical tools are needed for this property. I will begin with the property of boundarylessness, and for this we need the tools of formal models, reduction of germs, and from this, using these tools, we establish boundarylessness. So what do we do? Yeah, maybe first let me give a quick introduction to formal models. We have our K non-Archimedean field. Let's assume it's non-trivial regulation. And Yang gave the remark, whether we have trivial or non-trivial regulation, it doesn't really matter. We are free to take any field extension. So let's just assume non-trivial regulation. And then we have K naught, the ring of integers, and the K tilde, the residual field. Okay, so for example, if K is the field of Laurent series, formal Laurent series, then ring of integers is power series, and the residual field is just the C. And if K is the p-adic field, then K naught is the p-adic integers, Q tilde is FP. So for our purpose, we can just focus on the first example, and also extensions of this formal Laurent series field. Yeah. So Renault's theory of formal models can be summarized in just one theorem. This is the theorem. So we consider the generic fiber functor is the eta that goes from this category of formal schemes, locally topologically of finite type, over the ring of integers to the category of rigid K-analytic spaces. Yeah, locally topologically of finite type, it just means that locally you can write it as any rings that are generated topologically by finitely many generators, and that's all. And then we have the generic fiber functor. It's easy to imagine. It's just take a tensor product with K over the ring of integers. And Renault's theorem says that this generic fiber functor induces an equivalence between the subcategories. First is the category of quasi-paracompact admissible formal schemes over K naught, and also localized by the class of admissible formal blocks. There's a lot of non-Archimedean jargon here, but they really have not much meaning. Quasi-paracompact it just means that local finiteness condition. Admissible means this locally topologically of finite presentation plus flat. And there actually, once we have flat topologically of finite presentation and the topologically of finite type, they are the same thing. If you remember what you learned in commutative algebra, finite presentation, just the ideal is also finitely generated. So yeah, so we just have this subcategory, and then we quotient by admissible formal blow-ups, which simply means that we take blow-ups with centers in the special fact. So this doesn't change the generic fiber. And then taking the generic fiber functor, we this quotient category is identified then with the category of quasi-paracompact, quasi-separated rigid K-analytic spaces. Here, quasi-paracompact, quasi-separated, it's really very mild finite conditions. Oh, here when we say rigid K-analytic, it's in the sense of the classical rigid analytic geometry. It's slightly more restrictive than diatomics because diatomics allow radius that are not in the valued group, the root of the valued group. Here we only consider the classical because the general diatomics analytic spaces, they do not have formal model. Only take and rigid analytic spaces they have formal model. Okay. Yeah. So that is really the Renault's theory. Of course, Renault also has a theory about flattening techniques. That's not part of the theory, but the basic Renault's theory is summarized in this theorem. And that's for spaces. Unfortunately, this formal model theory, it does not apply to stacks, neither to the Riemann stacks or to Artin stacks, because stacks, they are given by this gluing using, because stacks, they are like glued using smooth or État and when we consider formal models of smooth and État morphisms, they are no longer smooth or État. So this theory of formal model just do not extend to stacks easily. Yeah, since they do not extend to stacks, then I have to prove this in order to bring the tools of formal models to the study of this non-Archimedean curve counting. I proved that although in general it does not extend to stacks, but it can still work for the stack of stable maps that we are interested in. So so for stable maps, let's consider curly X a formal scheme, locally finite representation over K naught, and we consider a basic T, a rigid K analytic space, and a K analytic stable map into the generic fiber X beta over the base T. We do not have formal models on the nodes for this K analytic stable map, but we can have it after passing to a quasi-État covering of T. So up to passing to a quasi-État covering, there exists a formal model curly T of T, and then a formal stable map into this formal model X, which gives back the K analytic stable map when we apply the generic fiber function. So essentially, this says that although the formal models for stable maps do not exist on the nodes, but we can actually find a formal model after passing to some État covering. And then it's now we can just deduce two very intuitive consequences. First is that if I consider the modular stack of formal stable maps into the formal model, and then I take its special fiber, it's just the same as the modular space of stable maps into the special fiber. And next, if I consider the modular space of formal stable maps into the formal model, and I take its generic fiber, I get the modular space of stable analytic stable maps into the generic fiber. It just shows that this taking modular space or taking special fiber, generic fiber, they all commute with each other. So yeah, so these equivalences now they are very intuitive, but as you see, behind the equivalences it's actually quite a sophisticated geometry about about stable maps. Okay. Yeah. So the reason I introduced formal models is because formal models enable us to deduce analytical properties of the generic fiber from algebraic properties of the special fiber. And this is really a special feature of non-Archimedean analytic geometry that is absent in complex analytic geometry. So in complex analytic geometry, you know that when you want to group something, you just do complex analytic geometry. But in non-Archimedean geometry, to establish some property, usually you have two methods. Either you do analytic method, or you can use formal model and reduce the question to algebraic geometry. That's also how Renault started his project of formal model, because for Rosen, he had this vision that one can prove most of the things in non-Archimedean geometry using tools from algebraic geometry. Okay. Yeah, and one really powerful tool to do this, to deduce properties of the analytic space from properties of the model is this Temkin's theory, Temkin's reduction of germs. Let me introduce this Temkin's theory. Okay, so what do we mean by reduction of germs? So first, we introduce what does a pointed K tilde variety mean. It's very simple. It's just a K tilde variety and a K tilde field, big K, and then a map from spec K to D. So it's essentially just a K tilde variety with a point, which might be defined over a slightly larger field. And then we consider morphism of pointed K tilde varieties to be this commutative diagram. So that's all. And we denote the left vertical map by F eta and the right vertical map by Fs. Sort of, you think F eta is the map between generic points, and Fs is the map between these K tilde varieties. And then we consider the category of all such pointed K tilde varieties, and we quotient by the subcategory by the class of morphisms where Fs is proper and F eta is an isomorphism. So here we see that all we are really interested in is just this generic point, this spec K, and then somehow some like the smallest proper subset containing that generic point. So how do we get this kind of pointed varieties? For any compact K analytic space X and any point small x in X, any formal model curly X, we actually obtain an object in this pointed in this category. This category large K tilde. So for the for the variety, we take the special fiber of the formal model XS, and then for the point, we take the spec of the residual field of this completed residual field. So we have in non-Archimedean geometry, everything has a norm, and our residual field also has a norm. We can complete with respect to that norm. Then we get this curly H called the complete residual field. And now you can take a residual field of this residual field. Keel always complains to me about the residual field of the residual field. But that's what we can do in non-Archimedean junction. You can just take a residual field of the residual field. Okay. And yeah, so we take this double residual field. We get this point, nice point in the variety. Then by Renault's theorem, we see that its image in this category is independent of the choice of formal model. So we see it's something very nice because when we have a k-analytic space and we have a point in the k-analytic space, then the germ of that point, we can associate to the germ around this point something canonical inside this category, which is independent of any choice of formal model. Yeah. So if you think that this thing is a bit artificial, this category, the definition, because it's some quotient category, actually there is a much nicer geometric interpretation in terms of classical Riemann-Zariski spaces. But it will just take me longer time to introduce the Riemann-Zariski spaces if you haven't seen it before, so it's easier to do this with a quicker definition. But one can do it by Riemann-Zariski spaces. Okay, so what does Temkin say about this reduction? So he proves that first, a k-analytic space X is good at a point small x, a point X, if this point. So first, what does good mean? Good means that this point little x has an affinoid label. It's not always true because analytic spaces, non-Archimedean spaces, sometimes like you may have this kind of corner and it may not have an affinoid label. So here, Temkin showed that the space is good at a point if and only if the reduction is affine. So this is actually the most difficult step for the properness, is to show this goodness at this point. And next, Temkin showed that a morphism of k-analytic spaces is separated at a point y, little y, respectively y lives in the interior. So this is the definition of interior I gave answering Ian's question this morning. If and only if the reduction morphism, so the morphism after we apply the reduction factor is separated or respectively proper. So here we see that we can turn the question of separateness of the generic fiber into questions of separateness of the potential fiber using this reduction factor. And similarly, we can turn the question about interior and the boundary of the generic fiber into properness of the special fiber. And by properness or separateness in this category of pointed varieties, it just means that the bits are separated for proper model. And one can show that equivalently in this case, all the models are separated. Yeah, so just this is a powerful tool to relate interior in the generic fiber with being, so it relates goodness of the generic fiber to the affineness of the special fiber. It relates separateness of the generic fiber to separateness of the special fiber, and it relates interior. Being interior in the generic fiber with the being proper in the special fiber. Okay. So these are just it's a very general story about non-Archimedean geometry. Do you have any questions at this point? Otherwise, I will just go on. It's strange that the color is different on my computer and on the screen. On my computer, I have red, but the screen has no red. It's okay. I don't know why. It's okay. Yes. So now let's get back to the modular space of curves in this polluted target space. Yeah, we recall that we have our original long Calabi-Yau variety line, and now then we have an auxiliary Porta variety T, and we glue them along this gray subset G. So, and G is a closed polyhedral affine domain, where the non-Archimedean SYZ vibration is a trivial affine torus vibration. And we glue, we do this gluing. So if we do this gluing, we get a compact Hausdorff K analytic space, because we are gluing two topological spaces along two closed subsets. So it's still Hausdorff, but analytically it's not separated, because being Hausdorff and being separated is more than being Hausdorff. Being separated in geometry, we also want the diagonal to be a closed immersion. And we also consider a smaller h inside this gluing load G. We ask H to be an open polyhedral affine domain whose closure is contained in G. You know, when you do this, yeah, we are doing analytic geometry, so not that far from symplectic or differential geometry. Usually, you need to choose this kind of open subsets, this kind of chain of open subsets to do some compactness properties like that. And now we can apply Reynolds formal model theory, and we can just have formal models for everything. So I had this Y, T, G, D, H. We can find formal models for everything. So the gluing can also be done at the level of formal models, and then we can also glue the line boundaries. So if we can also glue M4 line boundaries, but we cannot glue it everywhere, because if we can glue M4 line boundaries on the generic fiber, that will just show the generic fiber is projective. It's not going to work. But still, we can glue M4 line boundaries on the special fiber. That's the best we can do, and that's all we need, because the use of M4 line boundaries is to be able to take degrees of our curves, and for this we only needed to exist on the special fiber.
So here, when is K to be the same question as this, or do you take any K with non-trivial valuation, or?
Here it's any K with non-trivial valuation. Yes. Thank you for the question. And now I'm just slightly getting more and more precise. When we count curves, before it was just this kind of curve. Now we also need to add some mark. Yeah. So let's be slightly more precise. We add mark points P1 to Pn. These are the points of the curve that touches the boundary of my long Calabi-Yau variety. And I also add a marked point little s to the circle big S. I add my marked point little s, and then I also add a marked point E to this tail, to the end of the tail. I add a marked point E. So here S and E, the letters are chosen to mean the start and the end of the tail is. Yeah. Because we want to somehow distinguish the body from the tail. That's why we keep these marked points. And in order to do that, we should also be a bit careful about the modulus of this pointed curve. So we want to consider the subset of the moduli space. So let's first consider the tropical moduli space. We want to consider the subset where this S leg and the E leg, they are connected to a same three-valent vertex. We don't want any other marked point to get between S and E. And then we consider curly V to be the pre-image of this V in the analytic moduli space of pointed curves. Here, just the curves. And the reason we do this is that in that locus, the marked points S and E, they are closer together. So I just use S and E. We can cut out this tail, and the rest will be the body. And then all the marked points PI will lie in the body. I just don't want any marked points PI in the tail, because the tail is just auxiliary. See, don't want anything to happen. So as I said, now for any curve there, we can now cut. I can cut it into two disks. So one is the body disk containing all the PI, and it's where all the interesting geometry will happen. And the other part is the tail disk containing just the endpoint E. And that tail disk is this auxiliary disk, which does the most boring thing. Doesn't contribute anything interesting. Yeah. Okay, so now let's introduce the moduli spaces. We consider M0 M bar VB to be the moduli space of stable maps of F, stable maps F into this Boulud target space, such that the degree is equal to D, and we ask that the marked point PI and E map to the corresponding divisors with the tangency at least some given number. And we also allow some components to lie in the boundary. So when we have components lying in the boundary, the associated tangency is thought to be infinite. Okay. And of course, eventually we don't want any component to go into the boundary. So we just introduce this subset where no components map to the boundary. First, we have to allow components to map to boundary, because otherwise we will. Because in order to establish some compactness, we should first have more freedom, and then we try to prove that we don't have these bubbles going to the boundary. Okay. Yeah. And now the real locus, the moduli space that we are interested in is this subset of this moduli space M0 and I should have put a bar M0 and 3D, where the domain curve has this property given by V. Recall that this property is simply asking that there is nothing between the marked points E and S. So we consider this locus M, and where we put the conditions that we had before. So we want the body to go to Y, the end to go to T, and the marked point to go to H. So here, G is the locus we do, and H is a slightly smaller locus in G. Okay. So let's just remark that the conditions body in Y and in T and Mark's point in H is equivalent to the condition that the open disk lies in Y, the open body disk lies in Y, the open end disk lies in T, and the circle lies in H. So this follows from the maximum modular principle. Why do we do this equivalent? Why do we do this equivalent definition? It's because, you know, for the equivalent condition, it's because the conditions before, the previous condition is this B mapping to Y, E mapping to T. So B is a closed disk and mapping to Y, and Y is closed in V. So when you have a condition that something closed mapping to something closed, you can't really say much about what's the locus satisfying this condition. So it's better to have something open mapping to something closed, or something closed mapping to something open. That's why we have the equivalent formulation using the maximum modulus principle. And now I can state the first result regarding properties of modular space. So with Sean, we show that first, this locus M, defined by these equivalent conditions, is the intersection of an open analytic domain and a closed analytic. And the second, we show that it actually has no boundary. So it's boundaryless. Okay. Yeah, as I said, so this is the first property that we show, this boundarylessness. And the idea is to use formal models for stable maps and use Temkin's reduction of germs. Now let me quickly explain the idea by some pictures. Recall we have this domain curve cut into two closed disks, and then we use formal model. We also have we look at a special fiber of formal model for the domain curve, which will be this kind of tree of rational curves. Yeah. And then we consider this formal model of modulus X that I introduced before. Now we can rephrase the conditions about this body goes to Y and goes to T and the circle goes to H in terms of stable maps into the special fiber of the formal model. And then we see that the corresponding locus in the modular space of stable maps to the special fiber is now the intersection of a Zariski open and a Zariski closed. And finally, we use this so-called anti-continuity property of the reduction map for these formal schemes, and we deduce that the locus we are interested in is the intersection of an open analytic domain and a closed analytic domain. Okay. Yeah, and for the part about the boundary, we need to replace this non-separated special fiber by a smaller proper subset. So we no longer glue along the special fiber of formal model for G, but now we glue along the special fiber of the formal model for H, and we get something projected. Yeah, this is again something pretty nice, because in the generic fiber, after doing this string gluing, we just lose any projectivity, but somehow we can still have projectivity for the special fiber, and that's something necessary to get properness. So then we can rephrase the conditions that body goes to Y and goes to T in terms of stable maps into this proper projective special fiber. And now we can use the projectivity properness of the moduli space of the stable map in algebraic geometry. That's established by constraints. Also in the notes, more detail in the notes by Boundarylessness and the Porta Boundarylessness. So now we have a proper moduli space following from algebraic geometry, and we apply Temkin's reduction of germs. We deduce that the analytic moduli space has no boundary. But that's all we can get from the properness in algebraic geometry. All it can show is just without a boundary for the analytic moduli space. For the moment, it doesn't show directly that the analytical moduli space is also proper, but it gives us some boundaries. Now we have to work more to have other compactness properties, and only combining compactness with boundarylessness we can get properties in analytical geometry. Maybe I should say that in analytical geometry, properness just has a bit more meaning, because like in analytical geometry, proper is really two things. It's without boundary plus compact. So for example, a closed unit disk is compact, but it's not a proper. That's not something you want to call it a proper. And an open unit disk has no boundary, but you also don't want to call it a proper. Only when you have both, like you get a projective line, then you call it a proper. So it's something. This is the properness in analytic geometry has two parts. And of course, it still has the usual part about being separated. Okay. Yeah. And now let me say something about compactness. So we just talked about this part, this boundary. Now let me say something about compactness. For compactness, we have to consider an alternative boundary condition. Yeah. So recall that we had decomposed our domain curve as union of two closed unit disks. And now for compactness, we will thicken this circle into an open area A. So A is defined by the inequality that the norm of x lies between 1 minus epsilon and 1 plus epsilon. And we also introduced two new mark points, A and B, on the boundary circles of A, just to remember the places where we will cut the curves. And now we can decompose the domain curve as union of three pieces: the open disk B, the open annulus A, and the open another open disk E, the end open disk. Yeah, so similar to the locus V we considered before, now we have to consider this locus V prime, where it makes sense to cut the curves. And we denote by M prime this locus where we have the body open disk going to Y, the end open disk go to T, the annulus go to G, and the marked point goes to H. So yeah, so now we proved that this locus is now a closed analytic domain. And furthermore, this map phi taking stabilization of the domain curve and evaluation of the marked point S is topologically proper. It's just a relative notion of compact. So topologically proper means pre-image of compactness. So this is the compactness part that we established. Yeah. So the idea of group is similar to the case of to the proof for boundarylessness. So there we show that the corresponding locus in the special fiber of the formal moduli space is directly open, and the corresponding map for phi in the special fiber is separated and of finite type. And again, we use Temkin's reduction to relate separateness of the special fiber to separatedness of the generic fiber. And then when we have something of finite type and the special fiber at the level of generic fiber, let's get this topological problem. Yeah. Okay, so now we have established boundarylessness and the compactness. Combining them together, we should get properness. That's what I will talk about now. Yeah, let me just recall, we had many modular spaces and many different loci. So I have my modular space, this locus M, given by the condition that closed body disk goes to Y, and disk goes to T, and marked point goes to H. Then we consider this different locus M prime, given by the condition that body disk goes to Y, and disk goes to T, and area goes to G, and the marked point goes to H. So you see here, unfortunately, boundaryless is for one locus and compactness is for a different locus. And we must somehow put them together. We want them to be the same locus. So yeah, so first we just put some dummy marked points into M so that it has the same number of marked points as M prime. And then we really want that in some sense M should be equal to M prime. Because we proved the boundarylessness for one and the compactness for two. We want to combine them, they better be the same modular space. The observation is that the conditions for M and M prime, they actually become equivalent as long as the marked point stays away from walls in the essential scalar. And the thickness of this open annulus is sufficiently small. So once we stay away from the walls, we actually get equality from these two loci. Yeah, so therefore away from the walls, we have equality between these loci M and M prime. So combining the boundarylessness of M and the topological properties of phi for M prime, we deduce the properness that we want, properness of phi. So you may think that that's all we need. We get something proper, and that's the best. That's really the ultimate goal we want. But just remember that in our modular space, we still allow. We have been allowing components of the curve to go to the boundary, but we don't really want that. So yeah, so the curves we have been considering so far, they may have components mapping to the boundary. In other words, we have some bubbles. And we have introduced this subset, we denoted by M V naught D. The subset is the locus where no components mapping to the boundary. And now we want to talk. I want to talk about the result to eliminate these bubbles. So in order to, so now we want to extend the properness result to curves without these boundary bubbles. I think in below homology symplectic geometries worry a lot about the bubbles. Here it's the same thing we have to worry. And in order to eliminate these bubbles, we must now take into account the associated signs or the associated tropical curves of these non-Archimedean curves. So we consider this commutative diagram. We have the analytical moduli space, and we have this map phi taking modulus of the domain, the stabilization of the domain, and taking evaluation of the marked point S. And then we also have this sign map, because I have an analytical curve I mentioned in the morning. The analytical curve is this tree, and we have marked points. We can take convex tau of the marked point, and we get a span in the essential scale. Then for spines, we can also take this span. Then we get the associated tropical. The tropical moduli space, the moduli space of the tropical curves, and the essential scale. So this is this basic commutative diagram. We have phi taking modulus of domain and evaluation upstairs, and downstairs we have the tropical version for phi. Yeah. So we prove that now if I fix any S a transversal phi in the essential skeleton, then there is an open connected neighborhood WS of S such that the restriction of phi to WS, and also you restrict the image. You restrict both the domain and the image to WS. You get we get a proper map. And here we eliminated all the bubbles at the boundary. Yeah. So really, the real concept behind the theorem is really the elimination of bubbles. And the key lemma for preventing bubbles is the following. So when I have phi, any map phi from this to this moduli space restricted to WS, such that the image of this punctured disk. So I have a map of phi from this to this moduli space, possibly with bubbles. And I assume that outside the zero, it has no bubbles in the boundary. Then the claim is that at the zero, we also don't have any bubbles at the zero. Yeah, I wrote some pictures for the idea of the proof. Maybe I don't have time to talk about. So we just the idea is to consider this family of curves, and then we cut out some small caps from this family, and then we show that we have some compact analytical domain, so that the boundary of each cap of every fiber lies in this compact analytic domain. And then by the maximum modulus principle, we can show that this controls the body to lie in this compact domain K. And finally, we show that there will be no bubbles at the caps as well. Yeah. Okay. In the remaining 5 minutes, I'll talk about the last problem. So we have talked about boundarylessness, compactness, and the properness. It remains us to talk about the smoothness. For the smoothness, we need to use the non-Archimedean deformation theory. Yeah. So a distinguished feature of non-Archimedean enumerative geometry versus the logarithmic approach is the freeness of the analytical curves. Because in the log approach, when you degenerate, there's no more smoothness one can expect. So here we establish the smoothness of the moduli space via non-Archimedean deformation theory. Let's recall that the deformation of spheres locally is governed by the deformation of rings, because P is that the gluing of spectrum of rings. And similarly, here the deformation of K-analytic spaces is locally governed by the deformation of affine algebras. But the deformation of these finite algebras is just trickier due to the addition of analytic structure. You can take a look at the book by Garber and Romero. So since Model Porta and we already developed a general theory of derived non-Archimedean geometry based on Lurie's work on free geometry and structured topway. We will simply apply this more general and more conceptual machinery to the deformation problem here. Here, the deformation problem we consider is very classical. I think one may be able to do it following the results in Garber and Romero too. But we already have the more powerful and conceptual machinery. It's just easier to use this modern language. Yeah. So the central notion in non-Archimedean deformation theory is the analytical potential complex. The potential complex includes analytical derivations. Yeah. So let me recall what are derivations. Recall from commutative algebra, if I have an algebra, K algebra A mod M, then a derivation of A into M is a K-linear map B from A to M, satisfying the Leibniz BAB equal to BBA plus AB. Yeah. So, but unfortunately, it's not that easy to generalize it to analytic geometry or derived analytic geometry. The Leibniz rule is problematic in derived analytic geometry for two reasons. First, the Leibniz rule implies that for d of fa, for any polynomial f, we have dfa equal to f prime aba. And in analytic geometry, we want this equality not just for polynomials, but also for all convergent power series. This means that we have to add infinitely many new rules. And second, in derived geometry, we are also obliged to impose the Leibniz rule up to homotopy. And then it will involve an infinite chain of higher homotopy. So somehow, instead of a simple equality of Leibniz rule, now we will have infinitely many Leibniz rules. Yeah. So the solution is to use split square zero extensions that one can define using some formal machinery in this derived geometry. And using that, we define the derivations in the analytical world. And we define the analytic potential complex to be the object. Yeah, so with model, we proved that this derivation functor is actually representable by an object, an OX module, and which is the analytical potential complex. And it turned out that this analytical potential complex satisfies all the expected properties, like compatible with identification, fiber sequence, Hilbert squares, closed immersions, and cosmical powers. Yeah, so using this non-Archimedean deformation theory, now we deduce the smoothness of moduli space. We had this properness 5 minutes ago, and now using the deformation theory, we can further prove that this map is actually smooth over a variety of the subsets. I guess that's all I want to talk about today. Thank you very much for your attention.